Going live now. So welcome back, everybody, to episode 39 of the Quantum Science Seminar, which today will be all about quantum fluids of light. And if you have any questions for the talk, we would like to hear them. Please send us your questions to quantumscienceseminar@gmail.com or use the YouTube live chat at the right or at the bottom of the screen. Please also note that, as usual, there's a 30-second time delay between what you see on YouTube and what we do here. And with this, I would like to hand over to our very special guest, Quentin Glorieux today, who will introduce our speaker today.
Hi, everyone. I'm very glad to introduce Jeff Steinhauer today. So Jeff, we get lucky to have Jeff in our lab as an inviting professor for 1 year in LKB in Paris. So Jeff has done his PhD in UCLA and then he did 2 postdoctoral positions in Weizmann in Near-Davidson group and then in MIT with Wolfgang Ketterle. And he's now a full professor in physics department in Technion, and he's been visiting us for 1 year now, and it's been a great collaboration. Jeff is really an expert in the field of analog gravity. He demonstrated the realization of sonic black hole in BEC back in 2010 already. And then 2 milestone papers, at least since that, in this field. One in 2016 with the first spontaneous observation of Hawking radiation, spontaneous Hawking radiation in the BEC, and measurement of correlation in this type of systems. And a very recent paper in 2019 with the observation of thermal Hawking radiation and measurement of the temperature in an analog black hole. So with this background, Jeff came to our lab to do this similar experiment in a field of light, and he will present this very recent result that we've been achieving last year in MCAB in Paris with the great and major contribution of Jeff.
Well, thank you very much for the introduction, Quentin. And yeah, it's been a pleasure working here in the LKB laboratory. And I'm going to discuss our work of analog cosmological particle creation in an ultra-cold quantum fluid of light. So this is an analog experiment. And within the analog experiment, I want to learn something about the real thing. So we'll start talking about by discussing cosmological particle creation. Then we'll discuss the ultra-cold quantum fluid of light. So this is a graph of the radius of the early universe. And there was first a period of inflation where the radius of the universe expanded rapidly. Then a photon baryon quantum fluid appeared, and the rate of expansion slowed down. Then even later, the photon baryon plasma recombined. So what is cosmological particle creation? If we consider a mode of the universe, as the universe expands, the wavelength of the mode increases. And so that means the frequency of the mode drops. So during inflation, at some point, the frequency drops below the expansion rate. And so the evolution becomes non-adiabatic. And then even later, the expansion rate slows down, so the evolution becomes adiabatic again, so that ends this non-adiabatic period, and during the non-adiabatic period, there's population of the modes. Now, after the modes have been created in this quantum fluid, the modes are acoustic modes of the quantum fluid. So these are the modes which have become populated. We can calculate the amount that was populated by assigning operators and having a Bogoliubov transformation. So we assign a annihilation operator B to the acoustic modes in the quantum fluid and A to the modes during inflation. And so there's a Bogoliubov transformation between the modes. And the beta coefficient, which is the important coefficient for particle creation, is non-zero when the modes have different frequency. So the frequency is lower in the quantum fluid than in inflation, and that's what's important for the particle creation. So now that we have this Bogoliubov transformation, we can immediately write down the population of the cosmological particles and also the correlations between the pairs. The cosmological particles are pairs, and so there are these correlations between K and minus K. So we see that the populations are a function of the populations and correlations before the expansion during the inflation. So we need the initial state, the populations and the correlations during inflation. So if we imagine that at the very beginning of the universe, that there was some populated mode, there were populated modes due to the huge redshift, all these modes would be redshifted to zero frequency. So other than zero frequency, it's considered that the modes should have been in the ground state. It should be vacuum. However, there's a slight problem with this picture. If we take a finite frequency mode and trace it back in time, at some point it becomes trans-Planckian. So, so it has a wavelength shorter than the Planck length, and no one knows how such a mode should evolve. But it's thought that even after the trans-Planckian period, there's enough time that the modes should redshift to zero frequency. So they should all the modes should be in the ground state. So in other words, all these pairs of A operators you can set to zero. And so the population is given by beta squared. That's the spontaneous contribution. So we expect a population beta squared of cosmological particles being produced in pairs. Now these cosmological particles are then going to evolve for some time tau, after which the plasma recombines and they stop oscillating. And then they'll be viewed at a much later time in the present day in the cosmic microwave background. So the way we see them in the cosmic microwave background is due to the phase relationship of the pairs. So if this is a pair, blue is one member of the pair and the green is another member of the pair as a function of position, and the blue is going one way and the green is going the other way, at the time of creation, they're created completely out of phase with this definite phase relationship. And for a shorter wavelength, this is some other mode with a shorter wavelength, it also has this phase relationship completely out of phase. But then when we go to the time of observation, these two different wavelengths are evolving with different frequencies. So while this mode might be out of phase at the time of observation, this other mode might be basically in phase at the time of observation. So that's what we're going to see that's going to let us see it in the cosmic microwave background. So here's the cosmic microwave background, the CMB power spectrum. And this is from observed by the Planck collaboration. So this is the newest observation. And so this is the power as a function of multipole L. So the multipole is the L of the spherical harmonics. So these are spherical harmonics across the sky. However, it's as explained in this article, if we map this back to the early universe, L maps back to a definite value of K. So we could think of this as K, as the wave number. So and we see these acoustic peaks due to the acoustic modes, the cosmological particles. So where there's a maximum, that means that at the time of observation, the modes were in phase, and a minimum means that the modes were out of phase at the time of observation. So it would be nice to observe some of this physics with an analog model to see that these acoustic peaks can really be produced by the process of cosmological particle creation. So there have been a variety of suggested systems, and all of them are in Bose-Einstein condensates. And we observe it in the fluid of light. On the experimental side, there was an observation, the Bose-Einstein condensate, as well as a pair of trapped ions. What's left to be done, and what our goal is to, first of all, observe the acoustic peaks. Second of all, compare them to theory, the theory of cosmological particle creation, and verify the mechanism of cosmological particle creation. So we'd like to create an analog universe. It should be some kind of quantum fluid, and it should have a rapidly decreasing frequency so that the evolution is non-adiabatic, and this should populate the acoustic modes. So now, okay, so I'll first introduce the system and then take some questions. So this is our system where we have a quantum, this is our quantum fluid of light. So there's a laser beam going through a rubidium cell, and the laser beam is the quantum fluid of light. And when the laser beam is inside the rubidium cell, there's an interaction between the photons, because the photons modify the index of refraction, and in turn, the index of refraction affects the propagation of the other photons. So there's an effective interaction between the photons. Furthermore, there's an effective time. The position along the laser beam plays the role of time. The time tau is given by Z over C. So now I'd like to take any questions that there are at this point.
So thank you, Jeff. So for the moment, we have one question.
Okay.
And this question is about what determines the choice of the quantum fluid that you want to use. So when you want to use light, BC, or why something else like ions?
Well, we're going to see that our fluid of light has a huge advantage in signal to noise over a Bose-Einstein condensate. And as far as ions, I think it's nice to use a quantum fluid, such as the fluid of light, as opposed to a pair of ions, because the early universe was indeed a quantum fluid. And so we could see certain things that one sees in the early universe, such as the acoustic peaks in the cosmic microwave background spectrum.
Okay, and we have a second question that just arrived. So asking, is the fluid three-dimensional or two-dimensional?
That I will get to, but it's three-dimensional.
Thank you. I think you can continue for the moment.
Okay. So we have this, as I said, just to remind you, we have this quantum fluid where the photons interact when they're in the vapor cell. So we can notice that at the moment that the fluid of light, that the laser beam enters the vapor cell, at the point where it enters the vapor cell, the interactions suddenly turn on. And when the interactions suddenly turn on, the Bogoliubov frequency suddenly goes up. So due to the interactions, so the repulsive interactions. So this quench of the interactions is analogous to I guess in that case it would be a contracting universe. Here, when laser beam exits the vapor cell, that would be analogous to an expanding universe, where the frequency suddenly drops. So there's a Bogoliubov transformation, and since this is a transformation between no interactions whatsoever to interactions, the coefficients are the very coefficients written down by Bogoliubov himself to diagonalize the Hamiltonian of a weakly interacting Bose gas. So now what we'd like to do, what we do is we image the fluid of light at some distance Z from the second quench. And so that gives some effective time after the second quench. And we acquire an ensemble of 200 images, and we compute the power spectrum. So, so here's one such image, and we're of the fluid of light. And so the entire fluid of light, the 100 nanosecond pulse, is integrated in the image. So since it's integrated over the axial dimension, when we take the Fourier transform of this, we're really getting the z=0 component of the Fourier transform. So we're getting a slice in K space. We could then, and this is the Fourier transform of the fluctuation relative to the average of all the 200 images. So now, when we take the magnitude squared and the ensemble average, we get the power spectrum, or the static structure factor, and where m is the total number of particles in the system. And the now this is the theory. This is the observation. To compare with theory, what we'll do is we'll make a Bogoliubov approximation and assume that the density fluctuation is a small fluctuation on top of a big background, in which case the power spectrum becomes the shot noise plus a function of the population and correlations of the quasi-particles. So now I'm going to show you at various effective times tau, the observation of the power spectrum. So here you could see as a function of time, the power spectrum shows these shrinking ring patterns. And these rings are the analog cosmological particles, the correlations between them, or the power spectrum. So where there's a bright ring, that's a point where the cosmological particles were in phase at the time of observation, and the dark ring is where they were out of phase. And you could see that the rings shrink with time. That's because a small k takes longer to come into phase. Furthermore, you could see that the pattern, that the first minimum agrees well with this green dashed line, which is the theoretical prediction, and we'll discuss the theoretical prediction more a little bit later. So we can also get plot a radial cut of this pattern, like this, as a function of time. And so these are the acoustic peaks. The black curves are the observation in the power spectrum, similar to the acoustic peaks in the CMB spectrum. So now we'd like to compare this to theory. So we need to know, what was the initial state? Is this spontaneous or stimulated? So in order to answer that question, first we'll find the initial state for the first quench. So to do that, we're going to look at the very low Ks. The very low Ks have a very low frequency, a frequency approaching 0, so they don't oscillate within the time of the experiment. So these low Ks are a window back in time, because any quasi-particles created in the quenches will not change this very low K point. So in this limit, the static structure factor, the power spectrum, becomes 1 plus twice the population of the quasi-particles before the first quench. So in order to extract this number at low Ks, we put all the curves on top of one another, all the black curves on top of one another. It looks like this. So here's all the power spectra, one on top of the other, for the various times. And looking here to low K, we see that for K approaching 0, the power spectrum approaches something at or below this green line, the green dashed line, which is, and this green dashed line is 1.4. So 1 plus twice the population is 1.4. So that means the population is less than or equal to 0.2. So the first thing we could say about this population is that it doesn't diverge, which implies that the thermal component is negligible, because if before the first quench there were a thermal population coming in and stimulating the first quench, then there would be the spectrum, the power spectrum would look something like this. It would diverge for low K. So we don't see that. Second of all, we notice that this number is less than unity, which implies that the spontaneous contribution dominates in the first quench. So we can apply this window back in time principle at low Ks to the CMB spectrum. And we see that the CMB spectrum also goes to some low value at low K, implying that the population during inflation were near their ground state. And this is in agreement with what we said before, that, that the modes should be redshifted to 0 frequency, and so they should not be populated. So in summary of the first quench, we found that the initial state is vacuum before the first quench, and the first quench is spontaneously, the particle pair production is spontaneous in the first quench. Now let's go to the second quench. The second quench for the initial state, there is stimulation, firstly by the first quench quasi-particles, meaning quasi-particles produced in the first quench are going to stimulate quasi-particles in the second quench. Second of all, there's the spontaneous emission, that as the beam goes through the cell, the rubidium cell, the beam is partially absorbed, which implies that there's spontaneous emission in all directions of photons. And from the absorption, we compute that the spontaneous emission should be 1.2 quasi-particles per mode. So this population of spontaneous emission is what shifts the static structure factor up. You see that this power spectrum doesn't oscillate about unity, it oscillates about some higher value that's due to these spontaneous quasi-particles due to the spontaneous emission. The static structure factor should oscillate about 1 plus twice the population before the first quench plus the population before the second quench. And so this is the 1.2 number that shifts this curve up. What we can actually get rid of this upward shift by making the laser pulse 500 times stronger and weaker and longer, as shown in this by this blue curve. So for the long weak pulse, the static structure factor, the power spectrum goes to unity. That's because the spontaneous emission has some finite coherence time. And if the length of the pulse is longer than the coherence time, then the spontaneous emission can no longer be considered to be quasi-particles. It no longer interferes with the main beam. Furthermore, we can look for a thermal distribution in our fluid of light, our interacting fluid of light. We could check if it has a thermal component. If it were to have a thermal component, then the first peak, the low K part, should become emphasized, like in this blue curve, and we don't see that in the experiment. So we can say that the temperature of the fluid of light is less than 2 mcs squared, where m is the effective mass of the photon, and cs is the speed of sound in the fluid of light. So this is similar to a Bose-Einstein condensate. So we could say our fluid of light is as cold as an atomic Bose-Einstein condensate. So in summary for the second quench is stimulated by first quench quasi-particles as well as the spontaneous emission. Now, if we include these two stimulating populations in the theoretical calculation of the analog cosmological particle creation, and we account for both quenches, we obtain these red curves. So these are the theoretical prediction, and we see that they agree well with the measurement with no free parameters. So we see that indeed the acoustic peaks seen can really be explained by the theory of cosmological particle creation. Another thing we can notice in these power spectra is that there's this sort of beating pattern. And this is due to the fact that the first quench stimulates quasi-particles in the second quench. And the envelope of the beating pattern should be sine of omega 1,2 tau 1,2, where omega 1,2 is the Bogoliubov frequency within the vapor cell, and tau 1,2 is the effective time difference between the quenches. So we could actually use this to plot points on the dispersion relation. We can pick off K just from this graph, just see where there are nodes and antinodes. And the nodes and antinodes should be given by the points where omega tau is an integer times pi over 2. So and from this equation, we could get the frequency, just knowing what the integers are. And so the integers are 2, 3, 4, and 5 for these points. And so that's how we get these blue points on the dispersion relation, and they agree well with the predicted dispersion relation. Another thing that we could do is look at individual modes of the analog cosmological particles. So here are the power spectra plotted one above the other for all the various times. And we see this complicated pattern, but we can understand it by looking at the looking along this dashed line and look at the values of the power spectra at the various points along this dashed line. If we do that, we get these curves that it simply oscillates as a function of time. It's just a sinusoidal oscillation, basically. And so this is, and it agrees well with the theoretical prediction shown by the green curves. We can fit sine waves to these oscillations and to put points on the dispersion relation for each of these individual Ks that we've plotted here. And so that's how we get these black points, and they also agree well with the predicted dispersion relation. Now what we'd like to do is to extract the density-density correlations for the cosmological particles. So far we've discussed the power spectrum, but we could also get the density-density correlations from the measurement. But in order to do that, we're going to have to know, is the fluid of, how many dimensions does the fluid of light have? And it turns out that it's 3-dimensional. We can understand that by starting with the usual nonlinear Schrodinger equation, which is written in the paraxial and slowly varying envelope approximations. And we see that the axial position z plays the role of the effective time. But there's these two terms which wouldn't normally appear in a nonlinear Schrodinger equation, this first and second derivatives with respect to the true time. We can get rid of these two terms by changing coordinates to a co-moving compressed coordinate. We could see it's co-moving from this factor, and it's compressed due to group velocity dispersion. So to get a feeling for this coordinate z prime, let's look at this example. This is a laser pulse, a square laser pulse, like we use in our experiment, traveling at the group velocity. And this is in terms of z. But in terms of z prime, it doesn't move, first of all. We're in the reference frame moving with the pulse, and it's compressed. So changing to this z prime coordinate instead of the true time here, what results with no further approximation, these two terms disappear and we get the 3-dimensional Gross-Pitaevsky equation, just like in an atomic Bose-Einstein condensate, where the 3 dimensions are x, y, and z prime. So now that we understand that the system is 3-dimensional, we could look again at our quenches. So here again is the laser pulse traveling through the rubidium cell. And here's this co-moving coordinate system, co-moving at the group velocity. The quenches happen at definite values of tau, at definite positions in the z direction. So the quenches happen at definite tau, and they quench the interactions in all 3 directions, in all 3 dimensions. So now that we have that information, we can realize that these power spectra are actually spherical shells, that this K is a 3-dimensional, is the radius of a sphere in K space, and these acoustic peaks are spherical shells. Now, in order to extract now the density-density correlation function, G2, we take the 3-dimensional Fourier transform of the power spectrum. And since we know that the power spectrum is spherically symmetric, the 3-dimensional Fourier transform reduces to this formula here. So plugging in these black curves into this formula, the density-density correlations look like this. So we get these black curves, and you could see that as a function of time, the correlations extend to larger and larger values of R. And this is because the quasi-particle pairs are created and then they move apart from one another to larger and larger distances. We could also notice that the magnitude of the correlations are about 10 to the minus 6, on the order of 10 to the minus 6. That means that the density fluctuations are on the order of 10 to the minus 3, the relative density fluctuations. That means 0.1%. So these are extremely small density fluctuations, and yet we have this very good signal to noise to see the signal. This is due to the optical system. Now, we can also apply this formula to the theoretical curves, and one gets the red curves, which agree fairly well with the experiment. So we think this is a nice way to compute the density-to-density correlations, is to first just write down the power spectrum, which is often easier to write down than the density-to-density correlation, and then just take the three-dimensional Fourier transform. We verify that this technique works by looking at this theoretical paper, which considers quenches very much like ours, and we can reproduce, and here's their density-to-density correlations. We can reproduce this graph using this equation. So in conclusion, analog cosmological particle creation has been observed in a quantum fluid, and we confirm the quantum theoretical prediction. The resulting acoustic peaks support the inflation model, since we see the acoustic peaks can really be produced by the rapid change in the frequency. We see that the pair production is spontaneous in one of the quenches and stimulated in the other. We find that the long wavelengths provide a window back in time, and we apply this to the CMB spectrum. And this suggests that the modes during inflation were in their ground state as expected. And we see that our quantum fluid of light is as cold as an atomic Bose-Einstein condensate. Thank you.
So thank you very much, Jeff.
You're welcome.
We have quite a bunch of questions for you.
Okay.
So the first one is from Morgan Harvey Lynch. So he's asking the following. So there has been some work, particularly by Leonard Parker and Ivan Agullo, which looks at the imprint of a pre-inflationary initial state and how it affects the distribution of particles created, with the hope of seeing the imprint in CMB or large-scale structure of the cosmos. Is it possible to perturb your system in some way prior to the expansion and study the imprint on the particle produced by inflection? This may provide a really interesting technique to get insight into the initial state of the universe.
Very nice idea. Yes, we could certainly do that. We just use vacuum. Our laser beam is essentially vacuum before it enters the rubidium cell, but we could certainly create a variety of states. I guess it'd be interesting to determine which state would be the most interesting from a cosmological point of view and try to create that state.
Okay. Very good. Then we have a question from Bill Phillips. So would you say that your photon fluid is a fluid of polaritons?
Wow, a fluid of polaritons. I have no reason to think that it would be a I guess I don't really know the answer to that question. From what I know about polaritons, I would say no, but I don't know exactly. I'm sure that if Bill Phillips is asking me that, he has a reason to think that maybe it is a fluid of polaritons. So I really have to think about it and get back to him some other time.
Yeah, so maybe a kind of very related question is how,
Yes.
I mean, the baryon photon fluid map to your system. And so, and also
I'm sorry, the what photon fluid? Say it again?
The baryon photon fluid, how
Yes.
it mapped to your, so what is exactly actually the mapping to your system? And also, I mean, which is more or less the continuation, do the boson in the quantum fluid have mass? And if not, how will the mass in bosons change this experiment, if at all? It's kind of a...
Okay. The first one, I'm not really familiar with this. I think we said the type of photon fluid that you mentioned. However, the issue of the mass,
So sorry, probably
effective
it
mass.
was not a good pronunciation. It's baryon photon fluid.
Baryon photon.
Yeah,
Ah, the
sorry.
baryon. Thank you. Okay. Okay. So can you ask the first question again?
So how do actually your system map to the baryon photon fluid?
Okay. It's a quantum fluid with acoustic modes, just like the baryon photon fluid, and it's can be in its ground state. So they're both, I'd say, a quantum fluid, something which is somewhere near its ground state. So it seems very similar in that sense. Microscopically, it's not exactly the same. It's photons rather than the baryon photon, but it does have these acoustic modes, which is the important thing. So that was the first. Okay, so that was the first question. The second question was the mass of the photons. One can show in writing down the Gross-Pitayevsky equation that the mass is played by essentially the wavelength of the light gives an effective mass. So if that answers the question.
Okay. And the last one was, how will massive boson change this experiment, if at all?
Okay, massive boson. So I guess what they're asking is about the excitation. I guess they're asking if the excitation spectrum had mass. Is that what they're asking? If the quasi-particles have mass? Maybe that's what
Probably. Probably yes.
Yes, okay. So if the quasi-particles have mass, I would think that it would greatly decrease the spontaneous production, because there's a maximum energy to the spontaneous production, you could say, given by the chemical potential, if you want. It should be some fraction, it should be a bit below the chemical potential of the condensate. So if the mass of the quasi-particles were significant, I think it could rapidly decrease the production. It'd be interesting to see this spontaneous production of massive particles, however. And with the optical system, we have such good signal to noise, maybe such a thing would be possible.
Then we have a second question from Bill Phillips. Is asking, could you explain more about how integrating over Z, which is like time, gives you a Z equals 0 slice? Does this mean a T equals 0 slice or something else?
No, it's a KZ equals 0. It's similar, it's just like tomography, like computerized tomography, to reconstructing a three-dimensional image from pictures, from two-dimensional pictures. So the fact that we integrate the system in one axis means that we get K equals 0 in that direction. And so that it gives us a slice in K space. I hope that answers the question.
Then we have another question. So do you see quantum depletion in this fluid?
Well, we should be able to see it, but we don't see it in this experiment, the effect of the quantum depletion. The quantum depletion should suppress this power spectrum at low Ks. And because the quantum, so we don't see this effect of the quantum depletion should be anti-correlated and should suppress the power spectrum at low Ks, and we don't see that. But one can imagine this type of experiment, one should be able to see such a thing.
So then another question. So all of the discussion was about spontaneous generation of bosons with the obvious mapping to the CMB. What will change if the generated particles were fermions?
Were fermions. Wow, I don't know. I don't know enough about the case of the early universe to know about the cosmological particles being created as fermions. I guess the question would be, would fermions create these acoustic modes in the baryon photon plasma? I do not know if fermions produce these acoustic modes. It's not hard to press me beyond my knowledge of the CMD spectrum. So I don't know the answer to that question.
Thank you.
Okay.
So then another question, is there losses in the medium? What is the influence of losses?
It's very important. There's absorption. We have 80% absorption as the beam goes through the fluid of light. First of all, that produces spontaneous emission, which we saw becomes quasi-particles and stimulates pairs in the second quench. Furthermore, due to absorption, as the intensity of the beam is decreasing, and that means the frequency, the Bogoliubov frequency is going down, and as are the Bogoliubov coefficients that are also changing. And so in order for the theoretical model, we had to include these evolving Bogoliubov frequencies and Bogoliubov coefficients.
Then another question from Bill Phillips is asking, what is the connection between excitation created by spontaneous or stimulated emission and the idea of excitation caused by non-adiabaticity?
Okay. The spontaneous emission was due to the laser beam being absorbed and re-emitted by the atoms in the medium. The non-adiabaticity, that's what happens at the ends of the cell. When the laser beam suddenly enters the cell or exits the cell, that's a non-adiabatic change in the frequency of the quasi-particles. So it's sort of in the bulk or at the ends.
Okay, so then we have a question from Heidi Hazan. So sometimes the S of K in your experiment has non-monotonic peak amplitude, similar to CMB experiments, where the peak near 800 is slightly larger than the peak near 500. Would you comment on this?
So the question, okay, let me see if I can go back. Okay, so for example, I guess they're asking the first peak being larger than the second peak, or the fact that, okay, so I guess I should go back to the CMB spectrum because they were using numbers. Okay, they said 800 is slightly larger than 500.
100, yeah.
Okay, well, the CMB spectrum has a lot of effects that we don't have, which might be causing this. There's the dark matter, there's all the propagation through the universe going from just after the inflation all the way to the present day. And so there are many possible effects that could cause this in the CMB spectrum. In our spectrum, the reason that we have sort of this beating pattern where the amplitude gets small and then big and then small and then big, that's because we have these two quenches. So I assume that it's really different, that the fact that this 800 peak is bigger than the 500 peak is not something that we're seeing, I would guess.
Then we have a question from Wenchao Xu. I wonder what is the effect of spontaneous emission of photons on the density power spectrum? How to distinguish between the dissipation and the dispersive effect?
The density power, the power spectrum, dissipation and the dispersive
effect.
Okay, I don't really know why. How does absorption? Well, we model absorption in our system. The absorption, you can, I guess, I'm just going to answer, what effect does absorption have on our system? Absorption, you can say, decreases the effect of the first quench to a certain extent, meaning if there were no absorption, this beating that we see would be even stronger because the first quench has been somewhat absorbed. However, I think, but the signal, these oscillations that we see is not due to absorption. It's slightly absorbed by absorption. So I hope that answered the question.
Then we have a last question from Bill, saying, you say that the quantum fluid is as cold as a BEC, but is in fact a Bose condensate? If not, what does it mean to be as cold as BEC, which I would think means a certain fraction of degeneracy temperature?
Okay. We're not saying that this is a Bose-Einstein condensate. What we mean, and what I mean by cold is from the point of view of being either quantum or thermal. Meaning when the quasi-particle population is very, very low, then you're left with just the shot noise, just the quantum fluctuations which dominate. So that's all I meant by as cold as a Bose-Einstein condensate. I meant it's dominated by quantum fluctuations just as much as a typical Bose-Einstein condensate.
Okay, thank you very much, Jeff. I think we can stop here with question, and I leave the space to Sebastian.
Okay.
Yes, thank you very much, Jeff, also from my side for a very clear talk and for answering very many questions in detail. Thank you so much.
Oh, you're welcome.
And I would like to remind everybody, wrap up here, remind everybody that next week on March 18th, we will have yet another seminar on a very different topic by Sabrina Maniscalco, talking about quantum algorithms. And you should certainly also check out our sister seminar, the virtual AMO seminar, where tomorrow they will have Hannes Pichler speaking about atom arrays. And finally, I'd like to announce our next hot topic session, which is going to happen on April 22nd. So if you would like to give a talk here, one of these 15 minutes hot topics talks, then please send us your nomination by email by April 2nd. And you can find much more information on our website, quantumscienceseminar.com. If you want to learn more, there's also, of course, the possibility of subscribing to our email list, to our Google Calendar. You can follow us on Twitter now. And with that, I'd like to thank you for your interest, and we hope to see you again next week, same time, same place. Bye.